Okay, so we'll finish this section off with an interesting example. Before you get too far into the details here, just look at the function first. You've got some function f, and it's defined as a piecewise function. So for the values of x that are less than 1, f of x is defined to be x squared minus 2. And for the values of x that are greater than or equal to 1, f of x is defined to be k times x plus 1. Well, wait a minute, what's k? That's usually not what we see here. Usually the rule should be entirely in terms of x, right? Because that's our function parameter. But we've got this unknown value k floating around. And, well, without knowing what that value k is, we can't really say that this is a completely defined function, and indeed that's the case. If you back up now and read the whole example carefully, it says find the value of the constant k, so the constant real number k, such that this function is continuous. Okay, well, think about it this way. X squared minus 2, that's a polynomial. So if you were just dealing with the function x squared minus 2, you'd have a continuous function. And same with kx plus 1. Even though we don't know what k is, kx plus 1, that's a linear function with slope equal to whatever k is, right, in a y-intercept of 1. But even more generally, it's a polynomial, and those are known to be continuous. So since this piecewise function is built from continuous functions, the only place where this function could fail to be continuous is right at the point where you're pasting them together, which is right at the point x equals 1. So that's the place where you need to check continuity. So, and like I said in the last example, whenever you're investigating continuity, what you want to do is take both of the one-sided limits and actually plug the value into the function as well. So we're going to work out three things, and I'm going to write them down before we actually calculate them. The limit as x approaches 1 from the left of f of x, then the limit as x approaches 1 from the right of f of x, and then f of 1, right? Just so we get a bird's eye view of how this is going to go. Those are the three things that we need to calculate. And really, if we want this function to be continuous, we need all three of these quantities to be the same. So let's start from the top. Let's work them out. The limit as x approaches 1 from the left of f of x. Start this out in the same way we did the last one. The first step should be to figure out what is f doing? What is f of x actually going to give us? Well, for values of x that are less than 1, because that's what's happening here, right? If x is approaching 1 from the left, x is less than 1. So f of x is actually going to be x squared minus 2, really, for the purposes of this limit. So let's do that as our first step. Okay, so that's our first step, but now we have the limit of a polynomial. So polynomials are continuous everywhere, so if you want to take a limit, just plug in the value. So you can just plug in 1, and you're going to get 1 squared minus 2. So that's going to be negative 1, right? Okay, so that's our first limit. Now take the limit from the right. Limit as x approaches 1 from the right of f of x. Our first step is going to be to figure out what f is doing. F of x is going to be kx plus 1. Because for the purposes of this limit, right, as far as this limit is concerned, the value of x is always greater than 1, because x is approaching 1 from the right. So that's why we know that f of x is going to be acting exactly like kx plus 1 for the purposes of computing this limit. Whatever k is, we still don't know, but it's some constant. That's all we care about. Okay, well, we don't know what k is, but we do know that no matter what k is, this is a linear function, or in fact, more generally a polynomial. So that means if I want to evaluate this limit, I can just take that value 1 and plug it right into the function. So I'm going to get k times 1 plus 1. Okay, if I simplify that a bit, I'm just going to get k plus 1, right? Okay, and then what about f of 1? Well, f of 1, you just plug 1 into the function. So plug 1 in for x. Which one of these inequalities is satisfied? The top one, right? That's what this is. The top one is what's satisfied when you plug in x equals 1. So we're going to get k times x, which is 1, plus 1. And that just works out to k plus 1 again. Okay, and here is the idea. Okay, this was the function value. This was the limit from the right. And this is the limit from the left. And what we need is for all three of these to agree. Okay, we need this one, and this one, and this quantity all to be the same. Well, it doesn't matter what k is. These two are automatically going to be the same because they're both symbolically the same, right? They're both k plus 1. So no matter what k is, this function is always continuous from the right. Probably something to do with the fact that the inequality was on the positive half of 1, right? That's probably why it was continuous from the right. But that's not what we were asked for. We want to find the value of k that makes this function continuous. So what value of k makes all three of these quantities agree? Well, you just need to solve the equation k plus 1 is equal to negative 1. So just solve, let's do it over here. Solve k plus 1 is equal to negative 1. What are you going to get? K is equal to negative 2. So therefore, f is continuous when k is equal to negative 2. And that's a complete answer to that question. So if you're doing a problem like this, there's one on the next lab worksheet. This is how you want to do it. You want to show all these steps very carefully. This is the way to completely do these problems correctly. You want to make sure you're showing clearly where you take the limit from the left of the function, limit from the right of the function, and you're plugging the value. In this case, the value we're interested in is x equals 1. You show exactly where you're actually plugging that value in. And then you're going to get three separate quantities. And then from there, it's just finding out where they're equal. So this was the easy part, right? This was almost, you could say, this is the fun part. Most of the work was done working these limits out. Okay, so that's continuity. In the next section, we're actually now going to, well, I won't say too much about it because I'll say it in the next video, but we're going to revisit now the idea of slopes of tangent lines and the idea of a velocity function and the instantaneous velocity.